A point charge is a hypothetical charge located at a single point in space. From the name itself, you can make out that any charge which we can consider located at a single point in space, we have to start calling it point charge. You can say that the geometrical dimensions of the point charge is negligible. That means we cannot talk about its length, breadth or height or any volume. Now practically speaking, a body which is charged will obviously have some dimensions. We have a body 1 and a body 2, and obviously they have some size. Now if you look at the distance between these two bodies, I have taken it to be quite big compared to their size. That means the distance is very large compared to the size of the bodies which are carrying the charge. In this case, we can take an approximation such that we can ignore the shape or size of the body and replace the charges Q1 and Q2 with points, and we can call them point charges. So to approximate any charge to a point charge, the condition is that the distance between those charges must be very large compared to the size of the charged bodies. Now the reason why we studied point charge is because Coulomb's law is applicable only for your point charges. The statement of your Coulomb's law is the electrostatic force between two point charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between their centers. Now Coulomb's could come up with this law because of his experimental observations with electrostatic force. Mathematically, we can write the electrostatic force that we are talking about is directly proportional to the product of the charges. It simply means that if we have 2 point charges Q1 and Q2 separated by a distance r, the amount of electrostatic force, the attractive force and the repulsive force, depends on how big these charges are. If the values of these charges are small, then we expect smaller values of electrostatic force, and if these values of these charges are large, we expect greater or larger electrostatic force between them. Force we are talking about depends inversely on the distance. That's quite simple to understand because if the bodies are far apart from each other, the attractive or the repulsive force also will be less. So what does this actually means? It means that if we have two charges Q1 and Q2, point charges separated by a distance of 1 meter in your medium of air or vacuum or free space, then the force between them is found experimentally to be 9 into 10 to the power 9. Now if we double one of the charge, that means you have your Q1 and Q2, and suppose we make one of the charge double its initial value. That means now your Q1 is your 2 coulombs and your Q2 is still 1 coulombs. We are comparing these two cases. Clearly we have not changed the distance, and you will notice that the force will not be same but it will be larger because you can see we have a larger charge now or bigger charge. It is found that the force now will not be same as earlier, but it will be double the value of your initial force. That means the effect of making one charge double the value will also result in the force being double the previous value. So 9 has become 18. Also, if we simply triple the value of one of the charge, like here we have 3 coulombs of charge and the other charge is still 1 coulombs separated by 1 meter, you will notice instead of getting 9 into 10 to the power 9, which was the force between 1 coulomb and 1 coulomb of charge, we get now 27 into 10 to the power 9 newtons of force, which clearly shows that this new force is now 3 times the initial force. So the effect of making a charge or one charge triple the initial value should result in a larger force 3 times bigger than the previous value. Let's see what happens if we make both the charges doubled. Again, we started with 1 coulomb and 1 coulomb of charge, and suppose we have doubled them. That means this has become 2 coulombs and this also has become 2 coulombs. Notice the formula was Q1 Q2 by R square. If we double the first charge, the force becomes double. But since we have double the second charge also, now again there should be another 2 in front of it, which is going to result in the force being 4 times bigger than the initial value. That's why earlier we had a value of 9 to 10 to the power 9 newtons, but now when we double the value of both the charges, now we get a force which is 4 times bigger than the initial value, which is here 36 into 10 to the power 9 newtons. Coulomb's law also tells us the effect of the change of distance between the charges. Like for this case, we have 1 coulomb of charge separated by 1 meter, and the force is 9 to 10 to the power 9 newtons. But suppose if we increase the distance to double the initial value, we have the same charge, 1 coulomb, but notice we have now doubled the distance from 1 meter to 2 meters. The effect of this increase of distance must be reduction in the value of your electrostatic force. And it is found that the force now becomes 1/4 of your initial value. The reason is because the force is found to be inversely proportional to the square of the distance. So if we have the distance earlier to be d, but now we must have a distance not d but twice d. And when we square the twice d, we get 4d square. Clearly, if you compare it with the previous case, earlier we had 1 by d square, but now we have 1/4 of 1 by d square. Clearly, the force I can tell you is now new force, which is 1/4 of the initial force. So the effect of making the distance double between the charges should result in a force which is 1/4 of the initial force. And obviously, you can again continue in the same way and say that if we make the distance 3 times bigger, then the effect of that will be that the force will become smaller to a value which will be F by 9, because the square of 3 is your 9. And obviously the reverse is also true. If we halve the distance, the force should increase by 4 times. And if we make the distance 1/3, the force should increase by 9 times because of the square. Now, to remove this proportionality sign, we have multiplied by a constant which we call as constant of proportionality C. Now some of your schools might be using K, but I am using C. That is not a problem. You can use K as well. But later you will see that there is a property called dielectric constant, again for which we are using a symbol K. Hence for right now we have used the symbol C. So the difference between this and this formula is that the first formula tells you on what factors this electrostatic force depends upon. The second formula is going to tell you about the value of the force. And since it is only going to give us the magnitude of the force, the value of the force, we call it scalar form of your Coulomb's law. Now this formula, as you can see, we cannot use it because still we have not talked about your constant C. Let's look at this case to show you why this C is important. Suppose let's take up this case. Suppose we do not have the C in the formula, and we write F equals to Q1 Q2 by R square. And suppose we have a case where we have two charges. One is your 1 coulomb of charge and the other one is again 1 coulomb of charge separated by a distance of 1 meters. Experimentally, it is found that the force between these two positive charges is 9 into 10 to the power 9 newtons. That means two charges, 1 coulomb each, separated by a distance of 1 meter, should experience electrostatic force of attraction or repulsion, the value of which should be equal to 9 into 10 to the power 9 newtons. Now, if we simply use this formula without that constant of proportionality, we have to write F equals to Q1 Q2 by R square. We must write here 1 coulombs, we must write here 1 coulombs, and we must divide by 1 meter and then square it. Obviously, you will see 1 by 1 will be 1, so we have 1 here, and the units are going to be coulomb square meters minus 2. Obviously, this cannot be the answer because we already know that the force between 1 coulomb charge separated by 1 meter distance should have a value of force equal to 9 into 10 to the power 9 newtons. Using this formula without a proportionality constant gives us 1 coulomb square meter minus 2, which is not equal to the numerical value as well, and even the units are not matching. So clearly this cannot be the formula that we have to use. So we need to come and adjust this formula with some constant. Notice, if I use the formula where we write 9 into 10 to the power 9 Newton meter square and Coulomb to the power minus 2, and then multiply with Q1, Q2 and R square and apply in this case, you will see we will get 9 into 10 to the power 9 Newton meter square Coulombs minus 2. The Q1 is 1 Coulomb, so I write here 1 Coulombs. The other charge is also 1 Coulomb, so we write 1 Coulombs divided by R, which is 1 meters. Notice this Coulombs and Coulombs will be cancelled by this. This meter square will be cancelled by this, and we will get 9 into 10 to the power 9 newtons, and which is the correct answer. So clearly, as I told you, our formula should not be only with your Q1 Q2 by R square, because it does not give us the exact answer, but we should multiply this formula by a constant whose value is 9 into 10 to the power 9, and the SI unit of this constant should be Newton meter square Coulomb minus 2. And all this calculation that I've shown you is applicable when the medium between the two charges is air. The constant that we are using should have a value of 9 into 10 to the power 9 Q1 Q2 by R square. Now suppose if we take the two charges again, 1 Coulomb separated by 1 meter, but this time the medium, if it is water, it is found that we again cannot use the formula that we have for your air, because experimentally it is found that the force between the two charges when kept in water is not same as the force when they are kept in air. This force in water is found to be 80 times less than the amount of force that we obtain in air. Hence, the formula that we need to have when the medium is changed to water must look like this, which is your F equals to 9 into 10 to the power 9 divided by 80, because I told you the force is reduced to 1/80th times the value of force in air. And again we have Q1 and Q2 and then R square. So clearly you can see the constant that we are talking about, we got 9 into 10 to the power 9 and then we got 9 into 10 to the power 9 by 80. So this constant obviously is not an absolute constant which we can use everywhere, but depends on the medium where the charges are present. Again, if you compare to some other medium like mica, the formula should look like 9 into 10 to the power 9 and we must divide by 5, and then again Q1 Q2 by R square. So you see the medium has changed from air to water to mica, and the constant that we have has also changed from this value to this value to this value. What we are going to do next is that we are going to write this Coulomb's law in its proper form in various medium. The first medium we have taken is air, or let's say vacuum or free space. Now it's important for us to mention the medium, because you have seen that the electrostatic force is dependent upon medium. The force was different in air, in water and then in mica. And this air, vacuum and free space are considered to be almost similar, because a vacuum has no particles, free space is something which has no particles, and air is something which has very few particles. So all the three are taken to be equivalent, and you will see that for all the three approximately we can take the same constant. So we have this case, we have our point charge again, Q1 and Q2 located at points, let's say A and B, and you have seen we have written force multiplied by the constant that we need to write for this medium and multiplied by your Q1 Q2 by R square. Now this formula I have written is only applicable if I am choosing SI unit system. That means I am going to measure the charge Q1 in coulombs or write in coulombs, Q2 must be written in coulombs, R must be written in your meters, and finally we will get the force in newtons. If we change the SI system to CGS system, you will see the formula is going to change. For the time being, let's stick to SI system, and our medium is air or vacuum or free space. So clearly you can see our formula is this, and then 9 into 10 to the power 9 can be divided by 1. I'm keeping this 1 over here. I'll show you in a while what is the relevance of this 1. Now this formula is going to become a bit complex, so you need to follow me on this. So we are going from here, proceeding, and writing something like this. Now when you see this, you are totally going to be confused. Let's break. What have I done? I've written the Q1 as Q1, no change, Q2 as Q2 with no change, R square as R square with no change. But this number here that we must have has been written in a different form. We have written 1 divided by 4 into 22 by 7 into 8.854 into 10 to the power minus 12. When we do this, you will notice the value of this term here is exactly equal to 9 into 10 to the power 9. Now, you must be thinking why there is a need to do this. Now, writing in this form is very important for us because this 4 is written again as 4. 22 by 7 we know is your pi, but this number, however, we are writing it with a symbol called epsilon naught. Now, this epsilon naught is a property of our medium, which is air, or let's say vacuum or free space. If you remember, this whole thing had to do with your medium. 1 has nothing to do with the medium, 4 has nothing to do with the medium, pi has nothing to do with the medium, but this epsilon naught, now I can say that is the property of the medium. And for air, vacuum or free space, the value is 8.854 10 to the power minus 12. If you are to find the units of epsilon naught, you may write from this formula. Epsilon can be taken up here, force can be taken down here. So we got Q1 Q2 by 4 pi F R square. Clearly your charge Q1 and Q2 are coulombs, so we have Coulomb into Coulomb, which is Coulomb square. 4 pi doesn't have a unit. F has a unit of Newton, so we have Newton. R has a unit of meter, so we have meter square. That's why we got the SI unit of epsilon naught. So when we put that, we are going to write epsilon naught is equal to 8.854 10 to the power minus 12 Coulomb square Newton minus 1 or Newton inverse m to the power minus 2. Another unit you can see is Farad meter inverse. Now this epsilon naught that we have got by writing this constant 9 into 10 to the power 9 in this form is known as absolute permittivity of free space or vacuum or air. Now one more thing you can note here is that if you remember, I've written here is 1. This 1 below this 9 into 10 to the power 9, I will call it dielectric constant of air, vacuum or free space. And the symbol we can use is your K or epsilon R. Another name, instead of calling it dielectric constant, we even call it relative permittivity. That means if anybody asks you, what is the dielectric constant of air? You have to say it is 1. Vacuum 1, free space 1. Or if they are asking you relative permittivity, then also the answers are same. Now if you go to water and use SI system again, for this system where we have 2 point charges located again, let's say A and B, separated by distance r, we must write the formula as 9 into 10 to the power 9, but this time we must divide it by 80 and then write Q1 Q2 by r square. Because we know the force in water between the charges will be 1/80th the value of the force between the charges in air. Now again, just like before, this 9 into 10 to the power 9 can be written as 1 divided by 4 into 22 by 7 into 8.854 into 10 to the power minus 12. And this 18 is now written here. And we know this 4 is written again as 4. 22 by 7 is written as pi, and this 8.854 is written as epsilon naught. And again we have this 80 again appearing here. This 80 can be written together with your epsilon naught, and the formula will look like this. When we do that, I can say that this 80 times epsilon naught can be written again as epsilon W, where this epsilon W represents the absolute permittivity of your water. And this epsilon W is found to be 80 times the value of epsilon that we have for your air. Clearly you can see we are trying to write this constant that appears in front of this term in terms of the property of the medium. And epsilon W is definitely a property of the medium. And when we compare it to air, this epsilon W is found to be 80 times the value of your epsilon for your air, because of which you can say the force in that medium is 1 by 80th times the force compared to air. Again, if I ask you, relative permittivity of water is 80 or dielectric constant of water is 80, K is the symbol we can use, and I can say that the value of this constant for water is 80 times the value of your air. Now at this point you may be confused of what is going on, but let's quickly have a recap. Let's be very clear with what our medium is. If our medium is air, vacuum or free space, then the Coulomb's law is written as 1 by 4 pi epsilon naught Q1 Q2 by R square, where we know that we are using SI unit system. Q1 is measured in coulombs, Q2 is measured in coulombs, R is measured in meters. The value of this constant we know should be 9 into 10 to the power 9 because of experiments, where epsilon naught is the property of the medium and we call it absolute permittivity of free space of air or vacuum. The value of this epsilon naught is found to be 8.854 into 10 to the power minus 12 Coulomb square Newton inverse meters to the power minus 2. And the value of this epsilon naught is the lowest for any medium that we can talk about. Now because of the lowest value of epsilon naught for your air, vacuum or free space compared to other medium, the force between the 2 point charges is found to be maximum in air, vacuum or free space. So if our medium is water and our choice of unit is your SI system, that means Q1, Q2 again you can see are measured in coulombs and R is measured in meters, then we must write the formula as 1 over 4 pi epsilon W, which represents absolute permittivity of water. Now if it is air, you saw we have replaced here by absolute permittivity of air. It is water, so we must write absolute permittivity of water, and this epsilon for water is found to be 80 times the epsilon for your air. So we have written it to be 9 into 10 to the power 9 divided by 80 Q1 Q2 by R square. This 80, when you multiply with this epsilon naught, you got epsilon for your water. Clearly you can say epsilon for water is very large compared to your, or let's say 80 times bigger than your epsilon for your air. Hence I can say that the force in water will be less between the charges compared to the force in air. Again to tell you, the 80 that we got there is what is known as dielectric constant of water or relative permittivity of water. And the relation between this relative permittivity is that we can write absolute permittivity of water equals to relative permittivity of water times absolute permittivity of free space. Let's take up what happens when we take mica. Suppose we have taken now the medium as mica. That means the 2 point charges are kept in mica, not in air, not in water. Then we must have a formula where we write force equals 1 by 4 pi epsilon for mica, which is now we have to call it absolute permittivity of mica. Q1, Q2 are the two charges again. Charges are independent of the medium, so they do not change. Only the value of this constant over here or this value here is going to change. Notice I have written here 5 because the dielectric constant of mica is around 5, or let's say a bit more than 5. We must use a formula writing 9 into 10 to the power 9 and we must divide it by this 5. So again, if you ask me, the force between the charges in air will be greater than force between the two charges when they are kept in mica. To be precise, I can write force in air will be 5 times bigger than the force between the charges when the charges are placed in mica. So I hope you have got understanding of this, how this number 5 works and what is this called. Now again, if you calculate or write absolute value of mica, epsilon mica, 5 times the epsilon naught value. When we do that, we get 44.27. So this value of mica is greater than your epsilon naught, and hence the force in mica will be less than the force in air. So to wrap up, we can write the Coulomb's force as equal to some constant product of the charges divided by the square of the distance between the charges. And we have seen that this constant does not remain same for all the different media. Is because the force in those media does not remain the same. That means you can say that the electrostatic force is very much dependent on the medium. And you have seen that electrostatic force will be greatest in vacuum, it will be smaller in mica, and it will be very much small in water. And to talk about the dependence of this medium, and to talk about the dependence of the medium on this force, we bring a term called dielectric constant. And dielectric constant of air is taken to be your 1, around 1. Dielectric constant for mica, as I've shown you, is equal to 5. Dielectric constant for your water, we have taken it to be 80. The information which this K value gives is that the force between the two charges in water will be least compared to these two cases. Or I can say, since the K value is the lowest here, the force in that medium will be highest. Let's see now what happens if suppose we do not use SI system but we have CGS system. Our force will be measured in dynes. Our charges Q1 and Q2 has to be measured in stat coulombs, and our distance has to be measured in centimeters. In order that we get a correct formula to calculate the force, this constant is found to have a value of 1 dynes centimeter minus 2, 1 dynes centimeter to the power minus 2, stat coulombs to the power minus 2. Notice we no longer have to use 9 into 10 to the power 9 if we are following CGS system. And of course, when we change our medium to water, we must write F is equal to the constant which is 1 again. So we must just take 1 divided by 80 Q1 Q2 by R square, following the CGS system. And when we use mica, we must write F equals to 1 by 5 Q1 Q2 by R square. But don't worry, we do not need so much in detail about your CGS system. Just remember how the forces or the values of this constant are going to change if we change the medium. So what is the definition of this dielectric constant that we are talking about? So let's look at the definition of your relative permittivity or dielectric constant. Now when I say relative permittivity, I must mention the medium, or even when I say dielectric constant, I have to mention the medium. So we write dielectric constant of a medium may be defined as the ratio of force of interaction between the 2 point charges separated by a certain distance in air, vacuum or free space to the force of attraction or repulsion between the same 2 point charges or same distance apart in the medium. Now this definition may not be clear to you, but let me show you again. If you remember, for water the dielectric constant was 80, and I can say that the force in air, when I divide by the force in water, we know if we are getting a force of 9 into 10 to the power 9 newtons in air, we will get a force of 9 into 10 to the power 9 newtons by 80 in water. Clearly you can see this 80 has gone up, because of which we are writing 80. So the ratio of force between the charges in air to the force between the same two charges kept at same distance apart in water, this ratio is going to give us 80, and this is what we call as dielectric constant. So in the definition of dielectric constant, we must bring the ratio of these two forces, that is the force in air to the force in that medium, for which we are talking about the dielectric constant. Similarly, if I am writing the dielectric constant of mica, I must write force between the two charges kept in air divided by the force between the two charges when they are kept in mica. And we know the force in air that we are going to get will be 5 times the force that we are going to get between the two charges in mica. Hence, when we calculate this, we are going to get 5. That's why the definition of dielectric constant of a medium is ratio of the force of interaction between the 2 point charges separated by a certain distance in air to the force of attraction and repulsion between the same 2 point charges held at the same distance apart in that medium. Here you can see we have written the force between the two charges in air divided by the force between the two charges in a medium. We are writing the force formula in air, and we are writing the force formula in that medium. Since the two charges are same in both the mediums, so they get cancelled. Even the distance is same, this gets cancelled. 4 pi gets cancelled, 4 pi gets cancelled. Here we are going to be left out with 1 over epsilon naught. divided by 1 over epsilon for that medium. And when we take this up, we get epsilon for medium divided by your epsilon for air. And if you remember, epsilon for medium must be k times the value of epsilon for your air. Hence, when we cancel these two, we are left out with your k. Here you can see we are doing the same thing. Let's talk about some important points or notes about your Coulomb's law. Coulomb's law is strictly applicable to your point charges. If the charges are not point charges, we should not apply your Coulomb's law. The next thing is that, which is very important, we are not allowed to use Coulomb's law if the distances between the charges is less than 10 to the power minus 15 meters. Let me show you what does it mean. It means you have two charges Q1 and another charge Q2, point charges, and the distance between them is found to be around 10 to the power minus 15 meters, or maybe let's say less than that. Then you are not supposed to use Coulomb's law. The reason I would say, when the distances between the two charges become so less, they start denoting nucleus. And inside nucleus, if the charges are present, we know there's another kind of force which we call as nuclear force. And this nuclear force is the strongest force in nature. And hence we can say we can ignore our Coulomb's law. Having charges 2 into 10 to the power minus 7 coulombs and 3 into 10 to the power minus 7 coulombs, placed at a distance of 30 centimeter apart in air. Clearly you can see they have mentioned the medium as air, and they have given the values of your Q1, and this I can say it is your Q2. They have also given us the distance R. So we have written the Q1, Q2, we have written the distance R, but since we are going to follow SI system, I have converted the centimeter into meter by multiplying by 10 to the power minus 2. And you know that Coulomb's law, when I want to use for air, we must write 1 by 4 pi epsilon naught. This epsilon naught, if you remember, was absolute permittivity of free space or air, the value of which is 9 into 10 to the power 9. And I know this is the value in SI system. If it was a CGS system, we should have written only 1. So when I put the value of Q1, I have put the values of Q2 here, I have put the values of R here and then squared it. The final unit will be newtons. Here I do not need to speak much, you just check the steps. And finally we are going to get a value of around 6 into 10 to the power minus 3 newtons. So we have calculated the force between the 2 point charges. Charges were given and the distance was given, and even the medium was mentioned. If suppose in case they do not mention medium in the question, then by default you can take it as air. The next question is your NCERT 1.2. The electrostatic force on a small sphere of charge 0.4 microcoulombs due to another small sphere of charge minus 0.8 microcoulombs in air is found to be 0.2 newtons. So you can see we have a medium air, we have 2 point charges Q1, Q2, one is positive and one is negative. Force between the two of them has been given. The force on the first charge due to the second charge, so we have written that. What they want us to calculate is what should be the separation between the charges. So obviously you can make out, we are going to use Coulomb's law. Before doing that, we are writing proper units, the SI system we are going to follow. So we have converted the micro into your coulombs by multiplying by 10 to the power minus 6. So we have written the first formula here. Force on the first charge due to the second charge equals to the formula for air, the constant for air we have written Q1 Q2 by R square. In place of this we have written 9 into 10 to the power 9, and we have even written the force value. Our job is to find this R. When I solve, we are going to get a root, of course, and we are going to get around 12 into 10 to the power minus 2 meters, which is around your 12 centimeters. So that's the distance between the 2 point charges. So here the charges were given, the force was given, but the distance was not given, and of course the medium was mentioned. Now the second part of this question, which is B, the question is what is the force on the second sphere due to the first sphere? We found the force on the first sphere due to the second sphere. but the question now says what will be the force on the second sphere due to the first sphere. Now to tell you, when we have written the Coulomb's law, we have written the force between the charges and we did not mention the first charge or the second charge. What it means is that force experienced by the first charge due to the second charge is going to be equal in magnitude to the force experienced by the second charge due to the first charge. That's why if I have to write the force experienced by the second charge now due to the first charge, it is again going to be same, which is your 0.2 newtons. The next question that we have is NCERT 1.12. The question says two insulated copper charged spheres A and B. So we have drawn here copper sphere A and copper sphere B. Have their centers separated by a distance of 50 centimeters. What is the mutual force of electrostatic repulsion if the charge on each is 6.5 into 10 to the power minus 7 coulombs? The radii of A and B are negligible compared to the distance between the separation. This information helps us to say that the charge we are talking about is the charges we are talking about are point charges. The charges that we are talking about are point charges. Hence, we can apply Coulomb's law. So it's a simple one. You can say we have written the charge on the first, we have written the charge on the second. They have given equal. Distance has been given. They have not mentioned anything, so we can take the medium as air. So we have written the distance in your meters. Charge A and B we have written. We've written the Coulomb's force here law, and it's simple, and you got this value. Now if you read, what is the force of repulsion if each sphere is charged doubled the above amount and the distance between them is halved? Now this you can do directly, because you have seen if each charge is doubled, then we know that whatever force we got in the earlier case, the force now must become 4 times the previous force, because each charge is doubled. Also, notice that the distance also is halved. You have seen if the distance becomes halved, then the new force because of that must become 4 times the previous force. So the effect of making both the charge double and the effect of making the distance half is 4 times F and again 4 times F. If you combine both the effects, the new force that you should get must be equal to 16 times the original force. So what you can do now is that come directly multiply this force that we have already obtained by 16 and say that that's the new force. Or you can even show by using this method, where we are writing the new charge to be QA dash, which is double of your QA. QB dash is double of your previous charge, which is QB. The new distance that we have is your R dash, which is half the initial distance. So the new electrostatic force we must have is, so the new electrostatic force that we have must be F dash, the same constant of course, new charges and new distance. So you see we have written the corresponding values for them, and notice we got a 16 over here. Hence we have this value. The next problem. Two identical metal spheres having an equal and similar charges repel each other with a force of 103 newtons when they are placed at 10 centimeter apart. So they have given two metallic spheres, let's say Q1 and Q2, 10 centimeter apart, and they have given that they are equal in magnitude. The values are same. Similar means if one is positive, the other is also positive. What else is given in the question is that they have given force, they have given the distance, they have also given the medium in which the two spheres are kept, and that medium is found to have a dielectric constant of 5. When I use Coulomb's law now, I must write as usual 1 by 4 pi epsilon naught Q1 Q2 by R square, and obviously since the medium is not air, I must also divide by K, which is known as dielectric constant of the medium. We have written the force 103, we have written the value of 1 by 4 pi epsilon naught, which is 9 into 10 to the power 9, and we have divided by the dielectric constant 5. Q1 and Q2 are unknown, but we can replace the Q2 by your Q1 because they are same. Here we are going to solve for your Q1. So we are writing now your Q1 square, and we have all the other numbers. We take the q1 on one side and multiply the other terms left over and simplify the leftover terms. Then on simplification we get q1 to be equal to 23.9 into 10 power minus 6 coulombs, which you can also write as q1 equals to 23.9 microcoulombs. The next question is the distance between the two electrons. The distance between an electron, a proton in a hydrogen atom is 5.3 into 10 to the power minus 11 meters. So they have given a hydrogen atom, as you can see. Proton is present in the nucleus. It has some mass. Electron is revolving around the nucleus. Of course, it also has mass. We can treat the proton as your charge number 1, first charge, and we can treat the electron to be a second charge. So there is some electrostatic force between them. When you read the question, it says determine the magnitude of the ratio of electrostatic and the gravitational force between them. Since these two are charges, they will have electrostatic force, and since these two they also have masses, they will have gravitational force. So we need to find the ratio between these two forces. They have given the mass, of course, they have given the mass of proton and electron, they have given the gravitational constant, and they have given the value of E. So when we write the force of gravity, we must write the constant as universal gravitational constant, as you know, mass of proton, mass of electron divided by distance square. And when we write electric force, we must write this constant here. Since they have not mentioned the medium, of course, it will be air or vacuum. And of course, we have written Q1, Q2, which is your charge on proton and charge on electron by R square. We simply need to take the ratio because the question is asking us to find the ratio. So we simply put electric force divided by gravitational force. We have put the expressions, we have placed the formulas. The R in both of them are going to cancel because the distance is same in both the forces. And we simply have replaced this by your 9 into 10 to the power 9. G has been replaced by 6.67 10 to the power minus 11, the universal gravitational constant value. QP, QE, we have written QP, QE, mass of proton, and this is mass of electron. When we solve this, we are going to get around 2.27 into 10 to the power 39. Now if you write in this form, it shows that our electric force between those electrons and protons is so many times the gravitational force, and of course this is a very large number. 10 to the power 39, don't confuse it to 39 times. So our electric force is not 39 times larger than your gravitational force. It is 10 to the power 39 times larger or bigger, or let's say stronger than your gravitational force. If you remember, your nuclear force was the strongest, then comes your electric force, and the weakest force we have seen is your gravitational force.